Past 50 years is a story for generations to come. It has not been a cakewalk though. The country's population has doubled. Its energy demands quadrupled. The nation braved two severe global economic recessions as well. But when the going gets tough, we Indians get going. Today, Indian automobile industry, third largest in the world. But there was a time when conventional heating solutions and heavy reliance on imports created roadblocks for it. Our induction heating solutions paved the way for it to be in the fifth gear and keep pace with the ever increasing demand. From Bajaj Chetak to Royal Enfield Bullet, from Maruti to Mahindra and Mercedes. Our indigenously built induction heating solutions have played an important role in empowering Indian and global automobile industry to cater to Indian and international markets. There was a time when India did not have technology or forex capital. Many industries had to rely either on conventional production methods or had to pay heavy import duties, which was not feasible. And at the same time, consumerism was on rise. Consumers demanded quality products. Spillage, tampering was no more accepted. Our first of its kind hermetically sealed solutions help deliver customer expectations. Plastic packaged bottles and containers could be sealed, leaving no room for leakage, counterfeiting, or product recalls. Today, FMCG, dairy, pharma, and food companies are serving fresh Indian spices, beverages, personal care, medical products to Indians and global citizens. Indian pharmaceutical industry was facing a compliance challenge. Its medical science was ready for the US market, but it had to be US FDA compliant. Our made in India and first ever lab scaler machine helped Indian pharmaceutical companies with testing their products that made them US FDA compliant. From an import dependent country, we transitioned to an exporting nation even in pharma segment. Defense, aerospace, and nuclear are sensitive sectors crucial to strengthen India's global power. The country cannot be dependent on technology transfers and imports. The high-powered annealing machine built by us and used by Bharat Forge laid a solid ground for India's defense in form of Agni missile. Several of our indigenously built induction heating and welding solutions are used for battle tanks, submarines, put over bridges to manufacturing bullets and bombshells in Mangalyaan and Chandrayaan. Each and every made in India engineering solution has answered the call of industries. These solutions have saved billions in foreign exchange and energy consumption while enhancing productivity and reducing cycle times. These solutions have even inspired and encouraged 30,000 brands across 80 countries to choose us and to choose India for sourcing their engineering solutions. That is what we are celebrating today. The ingenuity of India and Electronics Devices Private Limited.
थैंक यू
इंडिया नेपाल को ऑयल देता है, उसके बाद भी इंडिया में पेट्रोल के प्राइसेस ज्यादा है और नेपाल में पेट्रोल के प्राइसेस कम।
I hope that's gone now. There's a background noise. All right. So now I have the pleasure of introducing our dear friend, George. Just give me a second so I can download that PPT. Quickly share. Is that visible?
Oh, it's different.
Right. Good evening, everyone. And I have the pleasure of introducing him for the nth time. And he's the marketing development manager at the Southeast Asia for Nickel Institute and is based out of Singapore. George is responsible for market development activities in the Asian markets outside Japan and China, executing projects, development opportunities, and managing partner relations in the region. Prior to joining the Nickel Institute in 2018, George worked for Thyssen, Essendal, and then for Bentler, where he undertook for the past 25 years a number of special assignments in Singapore and Asia Pacific region, including establishing organizations and joint ventures. A Swiss national, George studies marketing, economics, and commerce in Switzerland. And now I request him to hand over the post to him so that he can introduce our guest.
Okido, I try to share my screen, send request. Okay. Yep, I have it. I need to get the right screen. Okay. Oh, you should be able to see it now. Good. So, welcome to everybody. And yes, that definitely is true. Welcome to everyone around the globe. We have from so many different places, from different continents. It's absolutely fantastic to see you all in this fantastic webinar. And quickly introduction on the key sponsors on this. We have the Nickel Institute, and we are a global association of leading nickel producers. We promote the proper use of nickel in various applications, and we support markets for new and existing nickel uses, including stainless steel, while advocating for sound science, risk management, and socio-economic benefits in public policy. As you all know, nickel is still plays a vital role in over 75% of stainless steel. So our headquarters is located in Toronto. We have a research lab in Durham, the US, called Naipira. Then we have our Brussels office. They are especially on public policies, sustainability, communication, and market development. And then two subsidiaries, one located in Brisbane and one in Singapore. So there are as well two non-profit organization offices in China and Japan. Then the International Molybdenum Association, in short IMOA, is a global non-profit trade organization representing most of the molybdenum industry. They promote the properties and sustainable benefits of molybdenum in key alloying element of stainless steels and nickel-based alloys, especially enhancing corrosion resistance in various modern applications. And now the most important person of today, that is Dr. Graham Sussex. Graham is an expert in corrosion and material consulting with over 35 years of experience, serving as a consultant for the Nickel Institute for more than a decade. He brings extensive knowledge in stainless steel applications and standards. He has also been a technical specialist with the Australian Stainless Steel Development Association for over 20 years. He is active in ASTM and Australian standards development. and has significant contribution to the advancements in AS and ZSSD. This is the Australian standard and the New Zealand standards in welding for stainless steel. With that, I would like to hand over to Graham for his presentation, and everyone wishing you an interesting webinar and looking forward to your questions. Thank you.
Graham, you should be able to share now.
And I need to go back a couple. Okay, well, thank you, everybody. This is a rather marine picture, as you can see, and there's a lot of some copper nickel alloys there, and I'll talk about that in a moment. So just note the image on the left, that's 4 different columns, and then on the right is basically a whole lot of things sitting in the sea. And let's keep going now. There, that's right. Okay, the 4 strips there were in a UK harbour for 12 months. All of them were 9010 copper nickel, and the left trio, the ones which had all sorts of stuff growing on them, were connected to a cathodic protection system so that they would be protected. But of course, they were all copper nickel, so they didn't need it. But what that did was it stopped the copper from dissolving, which stopped the copper from preventing things from growing on them, and bingo, so they fouled up. The single panel on the right, freely suspended, not connected to the cathodic protection system, and so there was minimal fouling. And I'll just go back to that picture, and you can see that. Okay, so they're all the same material. The 3 on the left were cathodically protected, the other one wasn't, but it's the copper dissolving which actually gave you enough of a protection to stop the bugs landing. On the right, it's an offshore platform, and they clad the supports with 9010 copper nickel, 25 years in service and minimal fouling and minimal corrosion. And both of those images come from Copper Development Association Nickel Institute publication. Now, I'm going to talk about these things, the copper nickel alloys of interest are 9010 and 7030, and that's copper nickels, which include a bit of iron, a bit of manganese, maybe a bit of chromium, and some of the castings have niobium in them just for stabilization. The nickel copper grades are basically 400 series, the N04400 and the K500. And the difference between the two of them is that the K500 is a precipitation hardening material, often used for fasteners. I'll talk about that in a minute. So the composition of them is they're both about 65 nickel, both about 30 or 31 copper, 2% iron, 2% manganese for the 400, whereas the copper, the K500 one, has got manganese and 0.6% titanium. So they form a gamma prime, which actually stiffens up the, what do I do about questions? Just wait until the end? Okay, fine, I'll just wait till the end. Gamma prime in the K500 and make it very strong. I'll briefly mention, but not very much, the R405, which is a sulfur-containing free machining version of the 400 series, but really it's not used an awful lot. I'll talk a bit about corrosion resistance, mainly in marine environments, and then a little bit about welding techniques, including selection of consumables. So this is some tests done by various people, but it was in a harbour in the UK, and those pictures there were taken at year 1. I think I need to move that up to the top somehow. No, I can't. Okay. At 1 year, 2 years, 5 years, I think, How do I move the logo at the bottom? The thing at the bottom. Let's see if I can get it up. Yes, I can. Right. It's a 5-year sequence. So the carbon steel, the top was 3 months, 6 months, 18 months, and then the bottom it's 36 months, 48 months, and 60. And there was no protection. So basically they just got fouled up in a bad way. This is a 5-year sequence for 90-10 copper nickel, so 90 copper, 10 nickel. And we're looking 1 year in, 3 months, 9 months in the middle, 18 months across at the side. And you can see there is some fouling, but not big heaps, but certainly there is some. And then we go down to the bottom, 36 months, and it appears there was some sort of incident in the harbour, and you got a lot of particular seaweed type fouling because it's draped all over it. And then 48 months and 60 months, because by that stage it looks as though most of the basically protective copper has been covered over and it's just being fouled up. This is the same thing for 70-30 copper nickel. So a bit less copper, a bit more nickel. The first one looks very much the same at 3 months, 9 months, 18 months across the top row, and they're reasonably the same. And then again, across the bottom, you start running out of protection. Basically, because it's sitting in a harbour, there's nothing actually doing anything. And if you get any slime sitting on it, then basically the copper stops dissolving and protecting. This is some data looking at the maximum depth of attack around a blockage in various copper nickel alloy pipes in 12 months in seawater. And on the left, we've got 90-10, and the grey thing is with velocity of 2.1 meters per second. The 3.4 meters per second is the red, and the pale yellow, whatever it is at 4.3 meters per second. Now that's getting pretty fast for a copper nickel. For a stainless steel, it's absolutely nothing. But the difference is in terms of what gets swept away in terms of the copper, so that it doesn't actually stop the depth of attack going on. And notice that the attack depths there are up to 1 millimeter, not very much. This is a piece of 90-10 copper nickel pipe, which had perforated. Well, actually, it hadn't perforated. You can see on the left there the actual band where it's connected up, but it's certainly corroded. Probably, basically, this is what the report said, the iron was not in solution. It was actually came out in individual precipitates and rather mucked up the actual protective action. So that's what can go wrong if you manage to contaminate the copper nickel substrate with the wrong sort of metallurgy. This looks pretty, doesn't it? That is alloy 400. So it's a very high 65 nickel, 31 copper, so not quite so much copper, so you would expect a degree of fouling, except that that's a very, very resistant material in reducing environments, alloy 400. And I was going to show a picture of this, but I didn't. Okay, so around the centre, we've got a clamp, and we've got quite a severe crevice there, and it's corroded to an extent, but it's an alloy that works in reducing environments. So it goes to 0.2, perhaps 0.5 of a millimetre, and then stops. All those spots around it are where corrosion has started, proceeded for a while, and then stopped. So when you scrub that up, you'll find that you're looking at bare metal underneath. And that's quite a useful thing for an alloy. But remember, it only works in a reducing environment. So the initial corrosion, this is just corrosion, will continue, but not at a great rate. And that was, I scrubbed it out, it was actually for a year's exposure. This is looking at a 70-30. So there's less copper, more nickel, and O-rings were put around these, and you can see where they've been clamped at the end, and the protruding bit at the end has been attacked. But the black color is basically not corroding, it's just a copper oxide really. But underneath the gasket, you've got a bit of corrosion going on because it's not quite as good in a reducing environment. I have another picture of it, but I didn't think it showed particularly extra. But after 3 years, this is 500 hours of seawater flow.
Dr. Graham, is it possible for you to get a little closer to the mic or bring the mic closer to you? The voice is a little low on the lower side.
Okay, is that any better?
That's much better, yeah.
Okay, all right. Well, don't look at the picture because I'm leaning right into the phone. Okay, this is a 70-30 copper nickel, and in the crevice up there, there is just corrosion going on because it's not completely inert. But the service, 500 hours flowing seawater, 500 hours stagnant. Stagnant is when it starts to go badly. The next picture, which I don't have, after 3 years, showed that there was corrosion going on all across the whole surface, which is not bad, but just it was significantly beginning of attack. Okay, so let's talk about the fact that we're actually going to be doing welding on these alloys. And this is the sort of penetration that you get if you're used to doing mild steel, if you're using 12 chrome steels, stainlesses, then that's the sort of penetration you'd actually get. If you're looking at 304 or a super duplex, 7 or 8% nickel. And if you're looking at a Monel, that's a 400 or K500, then it's about 70% nickel, and that's about how far it would go through proportionately. So it's not that anything's gone wrong with the way the welding is going, it's just an inherent factor in terms of that. And those of you who use high nickel alloys will absolutely recognize this. So the higher nickel basically makes the whirlpool more viscous as well. So if you put the current up because you think it's just not quite hot enough, won't do anything except heat the whole thing up, and it'll take longer to cool down, and you may get issues with, at high temperatures, forming phases that you don't want. You'll have the interpass temperatures would go up, and you might get distortion. And the seed intermetallic faces is something that I actually said as well. So let's just look a bit at the welding. The copper and nickel are both completely soluble in each other. They're single phase, so you can't harden them by heat treatment because you can't precipitate something out and lock the microstructure up. You can cold work them quite easily, well, reasonably easily, but there will be some strength loss in the narrow band adjacent to the fusion line when you weld it up. Okay, so you've got a concentration at a point where it's a bit softer. But that's only really an issue on things like transverse bend qualification tests. If you're worried about that, then turn it around and do it for a longitudinal bend, but you may have to talk to your quality control people about that. The other components that are in there are a bit of manganese, about 1%-ish, as a deoxidizer or a desulfurizer. So they're basically taking out oxidizing agents, and some iron to give you erosion resistance. Or if you want more strength, you can replace some of the iron with chromium. I'll show you the actual numbers in a few minutes. Because of the lowish level of deoxidizer, if you weld them autogenously, then you may have a problem. There might also be porosity issues at that point. While there are matching filler metals, typically 70-30 copper nickel is used with, it's got about a 0.2% proof stress as 270 MPa, which is better than the 90-10 copper nickel, about 200. And it's going to be more noble compared to the parent metal. That's what you want. You've got the small weld surface is at a higher potential, and therefore it's protected by potentially any corrosion that might occur in the length of the pipe. And cleanliness is a lot more critical than for stainless steels. You can't allow for tooling crossovers from carbon steel or other materials that may put iron is a problem, but chromium can also be a problem. And you need to remove any cleaning residues, or even if you've got in your welding and you've got some condensation on it. One of the examples I came across was people using air blasts to actually clean stuff up and getting some condensation because their nice air blast hadn't been properly dried. And physical separation is a good way of making sure that if you're grinding something up somewhere, you don't put muck and rubbish onto your nice clean weld prep. The root pass has got to be free of contamination. Otherwise, you wind up with poor porosity there. And that's going to be encouraged by dilution from the parent metal because you're putting in a designed filler and you really don't want to have more parent metal coming in than normal. So you say, okay, let's make it a slightly larger root gap so you don't actually get so much of the parent metal coming in, or increase the amount of filler metal that you're putting in. So that's really getting the actual root level having decent corrosion resistance, decent properties. Very good gas shielding helps, but you probably need a reasonably large diameter ceramic, maybe even a gas lens. And certainly you're looking at reasonably short arc lengths because long arc lengths just encourage air intake. And that's bad news for making sure that you don't get contamination. Remember, we're talking copper nickel. We're not talking stainless steel. I mean, yes, stainless steel, it's an issue, but it's a little more sensitive with the copper nickels. You need to be careful about low melting point contaminants such as lead. That's not usually a problem. Phosphorus. So you probably want to have a look at the phosphorus and sulfur contribution that might come from the consumables that you're using. And carbon. Now that's usually just because of dirt and rubbish, but they all are contributors potentially for possible hot fissuring. And really, you want to look at an interpass temperature of no more than 150 or so, because you don't want the thing to stay hot for too long. The copper nickels have a high thermal expansion coefficient, so you need, when you're tacking them up, you need more than you need with stainless steel and more than you need with carbon steel. But it's not so much different because they are fully austenitic, not so much different from the ordinary austenitic stainless steels. And shield gas, argon, possibly some hydrogen to give you a higher heat input, but that'd only really be for the root, and the next few runs probably are best to be pure argon. You won't get quite the amount of heat, but still. And TIG welding gives the best quality. You'd normally use DC minus and pulsed current to get nice quality. Hey, I'm talking to welders, you know all this stuff. And for thicker sections, you might use MIG with argon or argon helium. And the filler wire is quite soft. So your runner friction's got to be low. And if the drive unit's a bit away, then you may need an intermediate feeder. But that's all adding places where you could pick up rubbish. So you want to be careful that you're not getting contamination. If you're doing MMA electrodes, generally basic flux positive DC, and hey, they've got to be dry, but then they're in their packet or they've been kept in an oven. If they get damp, dry it up to 250 or so. It depends a bit on the particular material. And when you're doing the welding, keep the weaving down. I mean, 3 or 4 electrode diameters is about the maximum you should ever want. And if you're looking at something that's more than about 12 millimeter, 12.5 millimeter, then submerged arc, yep, economical, provided you can make sure that the welding is horizontal, because otherwise, things tend to flow around a bit. Weld prep, pretty similar to the MIG, and just adjust the weld current down because you're using a bit adjust the weld current down for the lower wire diameter than the MIG, and choose the flux to make sure that it can be readily, my spelling is terrible, readily detached. And post-weld heat treatment, you usually don't need it. But if you do, you can do a stress relief, sort of 350 to 450. You can, but you don't normally need it. The nominal properties of the two, I mean, the 90-10, well, 10-ish nickel, 1.5 iron, you need a bit. The manganese is a deoxidizer, the sulfur is a deoxidizer, but there's nothing much there. And the phosphorus, you really can't get much lower because, hey, it's just there in the background. And typical mechanical properties, well, you can see the difference. I've mentioned those actually as a reason. Elongation, reasonably similar. And the hardness, well, the 70-30 is a bit harder, but not a lot. This is the reason why copper-nickel alloys are fairly easy. A copper-nickel is a solid solution. They're basically completely soluble in each other. So there's no problem with bad phases coming out of that. It's all in the other things that are in there. So you go from a liquid, you've got a bit of a band there, and then copper-nickel solid solution, totally soluble both ways. And of course, the reason why they tail off at the ends is just because it drops down a bit when you get to almost pure copper, almost pure nickel. So what happens when you actually weld something? You've got, basically, I've got the text on this on the next slide, but it's just here. You've got the weld pool, you've got an unmelted but melted but unmixed zone. You've got the fusion line just on the side of that, partially melted zone, the heat affected zone, which is out on the outside. And then you do a dilution sum and you work out what's going to happen in the weld pool compared with the sums that are in there, parent 1, parent 2. So it's dissimilar metals that you're talking about. Mind you, normally you're not talking about wildly dissimilar metals if you're sticking with copper nickels, but still. So you can control what you've got in the weld pool basically by choosing the right consumables. So those are the zones. The composite zone, complete mixing, and the unmixed zone, the parent plate melted but not mixed. Let's go back one. So the composite zone across the side, and then the melted but unmixed. The fusion line, yes, that's labelled, and the partially melted. And corrosion issues can occur in that zone basically due to dendritic solidification, long words there, especially if it's cooled slowly. And that just will give you differential things, particularly if you've got molybdenum in there, and there are some of the copper nickels that do have moly in them. And then you get the heat affected zone. So that's the normal heat affected zone on the surface. So the outside is on the right there, and unaffected base material. And so the thing that usually gives you a problem are those red areas there where the metallurgical issues happen. So what do you want to do? This is putting two things, excuse me, putting two dissimilar metals together, and they're not compatible. We'll look at in a second at the numbers that show that. But this is for carbon or low alloy steel, but it could equally well be anything that is sufficiently different to the second material. Put the buttering layer on, machine it into shape. The second metal set, which is in the buttered layer, is that. The reason why it works is because you're not having a large amount of heat in, so you're not getting a lot of the carbon or low alloy steel in this case into the actual weld zone. And it's basically the same as doing a weld overlay. You'll get some mixing, but not completely. Then you put the second gap, and then you go to welding and fill it all up as per normal. And so the actual welds that are going to be contaminated, weld metal that's going to be contaminated, is the one that is right next door and underneath the second and third and fourth and fifth passes. So it's I love the buttering word, basically like putting butter on bread. This is from AWS. It's in multiple volumes, and it's looking at weld metal and what you can have in terms of chromium. So if you're talking about nickel, then you can put 30% in. If you're talking nickel copper, then you're talking about 10%. If you're talking about copper nickel, then you're only talking about 5%. And nickel chromium alloys, and there are obviously some around, then you're looking at about 15%. And this is just in terms of forming phases that are going to be detrimental to the actual microstructure. This is hot shortness range for worrying about iron in the nickel copper alloys. And again, it's a simplification of an American Weld. Actually, if you look at it in the AWS books, it's pretty colors, but still we won't go there. And so in that hot short range, you have got basically iron rich intergranular deposits, and basically that makes the thing crack. Actually, it's not so much intergranular, it just goes straight through. So if you've got lots of nickel or lots of chromium, then you can stand things reasonably. Or if you have high nickel and chromium and copper below about 40%, then you'll be okay as well. But further down, the iron is just a problem. This is iron tolerance in welds by weld process. And it's basically the other one, but it's now broken down even more in detail, saying that, hey, it's going to matter how I'm actually going to measure this, how I'm actually going to weld this, and what process I'm going to do. And that can be an issue, and you can just decide, right, okay, on this basis, I've got to make sure that I use either TIG or MIG, or I can get away with submerged arc. Just basically, it will depend on what you've got and what you want to get. And again, this is for iron content. The previous one was that's for iron content. And up here, we've got chromium content. So they're also potentially a problem. So that's summarizing those bits. It means that you need to check the consumable composition versus the substrate. If you're copper nickel going onto carbon steel, you'll need a buffer layer of AWS 514. So it's ERNIC at 7 on the steel before you put down the next layer of the Monel. And Monel is just the high alloy, the copper nickel. Or else the iron contamination will give you hot cracking. But if you're talking about the 514 nickel copper 7, it's going to depend on the process. If you're talking at sub-arc, 2% iron dilution, but if it's gas shielded, can have up to 15% before you get hot cracking. And my understanding is it's because of the melted depth and how far down you're actually pulling up the metal to be actually contaminated. If you're looking at shielded metal arc deposits, to that can cope with about 30% iron dilution. That's pretty dramatic. And chromium, yep, nickel copper deposits only cope with about 8%, whereas copper nickel deposits shouldn't exceed 5%. Really means you need to look at the process as well as the composition. And I'm very sorry, but that's about it. It's a very likely once over, and that's the reason I provided this detailed set of references here. Copper nickel welding, that's freely available. The copper nickel fabrication 12014 and the guidelines both can come from the Nickel Institute publication. European Federation of Corrosion, that's perhaps a bit old, 2012, but was Carol Powell, who's unfortunately since died, Roger Francis, who's a guru on, well, stainless steels, I suppose, but it's also in high nickels as well. And the dissimilar metal welding stuff from Noel Herbst, who used to be the Nickel Institute person, sort of their technical person, can be downloaded from that link. The Stainless Steel Association in Australia has got it on their website. And I'm sorry, that's not nearly as much detail I was intending to put in, but I sort of ran out of time because of a few personal issues. So that's it.
I think it's quite crisp and very much to the point. We have quite a few questions already on.
Okay. What do we do? Go up and have a look at
We
the
can go
chat
up to the Q&A at the bottom, if you see.
Q&A. Okay, right.
Down. Next to the
Yeah.
share button, there's a Q&A.
Okay.
Next to the share, there's a Q&A button.
Yeah, okay. What? All right. The first two, I'm not going to throw at you straight off the top of my head. Can we have copies of these and we'll come back to you in a couple of days, okay? Because right off the top of my head, it's not going to go. The third one, what remedies to avoid porosities? Basically keep it clean, and that's really it. And stay within the limits of what you've got for the chromium or manganese isn't such a problem, but any of the points that I said before. Achieve 100 minimum before joining non-meg. Do we have any selections for weld consumable that can achieve 100 KSI yield minimum for joining non-mag drilling collar? Oh, I see. Okay. Consisting of P580 without any treatment condition. Why without any treatment condition? Oh, you don't want to restrict it. Off the top of my head, don't know. But come back. Next one, how nickel content affects weld penetration. It just does. It's, I think, a function of the actually movement of the, let me think, it'll be the bonding, you're breaking it down and it just is slower to go. Oh, that's it, it's the weld viscosity. So it won't come away from the surface so quickly. And that illustration of what happens with the different levels of nickel just shows from the amount of penetration that is what happens.
Is it possible to weld or braze copper without using an alloying material?
Yes.
Yes.
Yeah, you just use copper.
Copper to copper, yeah. You can do it with DC TIG as well. Need clarification about in refrigerant piping brazing joint using cupronickel material. Brazing should be performed using copper silver filler instead of a copper nickel filler as recommended by some international reference.
Depends where you are. The copper nickel filler, why would that be a problem?
I think it's also a matter of temperature, because in brazing, when you're joining two copper nickel pipes, if you have copper silver melts earlier.
Yes.
Therefore, you have a better joint. But if you do a filler wire with copper nickel as well, then the melting point will be higher and the base metal itself has the chances of getting melted as well. So that's one of the reasons why
you need to be a bit more careful about the welding. Yeah.
So it's in brazing, it's easier to use a lower temperature filler wire, is what my experience is.
Yes. Okay. You mentioned that copper ions are good for preventing biofouling. It's just they're poisonous. They're toxic to the bio, and so they don't try and land. They don't. Well, actually, they die before they get there, or perhaps they just avoid it because it's nasty. Why is chromium an issue? That's a very good question, and I went looking for that in the AWJ research bit, and I couldn't find anything on it. It's just, it is. And again, I'll go back and have another dig and then come back to that question. Kindly brief on cracking mechanisms on Monel 400 weld 450 to 500 oxygen service with very low possibility of sulfur contamination. No sulfur. What else could there be there? Monel 400, so it's, yeah, it's 7 should be okay. No sulfur contamination. Is it also, there is no other contamination there? Because you can get issues with chromium. Well, I've illustrated those already. No, look, I'll come back on that again. Well, kindly view below listed dissimilar material for GTRW words needs filler wire and technique suggestion. God almighty. Ah. So you want to join aluminium brass to copper nickel. No. Sorry, don't want to do that off the top of my head. And I'm not very much help tonight. You mentioned copper ions are good at preventing microscopic by muscles. Recently, that copper ions do not have a large effect on bacteria. Is this your experience opinion? No, it's not. It does have an effect on bacteria. Depends what the bacteria are, but it's in potable water. You can get copper. Let's think. In potable water that's stagnant, you can get deposits and you can get bacteria underneath it, and then you can develop a copper corrosion effect, despite the fact that there are bacteria around. You get, it's a thing called blue water, and it's something that happens in soft waters, but in hard waters, no. I'm not sure what the publication that you read it in, but I suspect it's probably in soft waters. Oh dear, the professor is asking me a question. Yes, okay.
I think the
That's
rest
going-
are, there's
that
one
is going to
question in the chat, I'm guessing there was one.
Oops, where are we?
Which we've covered, there was,
Where is it? Way down?
I have done PQR on 825 material 2825, and during G48 testing, my corrosion rate is 4. This is actually SAR service. There is a requirement of G48 test.
Hang on, where, how far? Oh, right down the bottom.
Right at the bottom, yeah.
Yeah, okay. And, whoops. PQR on 825 to 825. My corrosion rate is 4. What sort of shielding, gas shielding have you got when you're actually welding it up? Because usually that's the issue.
I think 825 to 825 would be still argon, and maybe argon plus 2% hydrogen. It's argon schedule.
That should be okay.
Yeah.
What sort of 825? What sort of heat tint was on it? Did they say, or was it cleaned up?
100% backing gas is also argon. What sort of a heat you are asking? Temperature?
No, I was asking what sort of, is there any heat tint actually on the surface? 825 is far enough up the nickel tree that I wouldn't have thought that would be an issue.
Yeah.
No, I'll come back to that. Sorry.
Okay. And then reference of welding process for alloy 400 overlay on a steel plate, GTAW or SMAW.
They'll both work.
Yeah.
TIG will be a bit prettier.
Yeah. Also, I think TIG will have lesser dilution compared to SMAW.
Yeah, because you're putting less heat in.
Yes.
Yeah.
So
Yeah.
if dilution is a concern, then TIG, else you can go with both.
Yeah. We can collaborate for cracking problem. Sorry, I don't understand that one.
I think that's some other thread of discussion from above?
Not sure.
There's one question that says we are from oil refinery facing issues of cracking during welding of copper nickel steel. Could you guide on repair methodology, please?
Cracking of
Mr. P. S.N. Swaroop. Copper nickel steel cracking is on the weld joint or
on the weld joint or to one side? Doesn't say.
maybe we'll take it up and I'll send these questions to you, and maybe when you have time, if you can reply back, we'll send a reply back to them.
Yeah, so what we'll do is we'll put it into the Nickel Institute thing and then send it to you rather than send it to the person direct, and you can
No, you send it to us and we will send it to them. We'll send it out.
Good, okay, fine.
Sachin, what you do is, Sachin, if you can just, collect all the questions from the Q&A and from the chat and send it as an email to both, so that once they compile the answers and give it back, we will reply back to the people who asked it.
Okay, we'll do it.
All right,
Yep.
thank you. So I think if that is all, we have, there is one more question coming in. If you are okay, we'll take one more question and then we can.
The porosity and hot cracking, that really is, the hot cracking is a function of looking at the consumable and what's in it and making sure that you're not going to go over the level that you can have for either iron, or iron's the usual one, or chromium if there's any there. And the porosity is, I'm sorry to say it, but it's usually an issue of cleanliness. So I'm not intending to insult people, but that's typically what it is. During hydrotest, 2-inch copper nickel joints found leaks. Yeah, what's the exact reason?
Could you repost your question, Mr. Muklivanan? He's getting he's finding leaks.
Leaks
in hydro test for cupronickel joints, and he found leaks near the weldment, I'm supposing.
Did he say near, or did he say actually in the?
1 second, I'll just go up and try.
During hydrotest, 2-inch copper nickel joints found leaks, and he's not saying whether it's in the actual weld or beside it. If you could clarify that and come back.
Okay. Leaks are near the weld joint in the HZ area.
Yeah, okay. Not sure. I'll have a think. I got a lot to think about.
That's always good.
Yeah.
So we will take up all the questions that we've not been able to answer. We'll post them back to the Nickel Institute, and I'm sure the team will send us the answers in due time. Please give them time to respond, and we will send the answers back to you.
Okay, good. Excellent.
All right. So thank you.
And can I just say
Yes.
that this bit on the last slide, there is a technical advice line that the Nickel Institute runs. So it's free. All you need to do is set up an account. Well, and that's easy. It's just basically saying your name and email and put the inquiry in, and it'll be fielded out to one of the Nickel Institute people around the world. Okay.
All right. So thank you very much for a very, very interesting, crisp presentation, Dr. Graham. And thank you, George, for always facilitating wonderful, knowledge-filled sessions. Thank you.
You're welcome.
And thank you, everyone, for participating and sending out interesting questions. We'll try to revert back as much as possible. All right.
Yeah.
Cheers. Everybody have a
Thanks
great
to everyone.
Yeah.
Okay, fine. Bye.
Bye-bye. Thank you.
Thanks. Bye.
Bye-bye.
Bye. Thank